something is awry in our understanding of the universe. Cosmology seems to be heading for a showdown on one of its most basic questions. How fast is the universe expanding? For more than a decade, two types of measurements have been in disagreement. Observations of the current universe typically find the rate of expansion, called the Hubble constant, to be about 9% faster than predictions based on early universe data. Researchers hoped that the James Webb Space Telescope, the most advanced telescope ever built, would help settle the question once and for all, but consensus has so far failed to materialize. Instead, the Space Observatory has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. The new physics needed to modify or even replace the 40-year-old theory is now a topic of debate. An exciting and interesting possibility is that there's something we don't understand about the universe. Join us as we dig deep into how new ultra-deep images from James Webb just confirmed there is something seriously wrong with our understanding of the universe. Our universe started with it bang, the Big Bang. Energy, mass, and space flashed into existence all within a fleeting instant. Then the young cosmos was formed, an expanding rowing plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other entirely, but scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched space to a small fraction of this matter safely from the fry. As the universe inflated like a balloon, the standard story goes that ordinary matter which interacts with light congealed around clumps of invisible dark matter to create the first galaxies connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density and therefore its expansion rate decreased, but then roughly 5 billion years ago galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant and inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter LCDM model of cosmology, which maps the growth of the cosmos and predicts its end, with matter eventually spread so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proved to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Offerla, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them, but an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly, faster than LCDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, said, "The only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be hoar by. Studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megapark. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megapark away from us, that means it will recede from us and us from it at 67 km/s at 20 megaparecs. This recession grows to 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,175 megaparecs away, it will recede from us faster than the speed of light. Second method to find this expansion rate uses pulsating stars called Psi-8 variables, dying stars with helium gas outer layers that grow and shrink as they absorb and release the stars' radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a SIFI it was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed sides into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating seats together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby seeds and cross-checking their distance based on pulsating light to that found by geometry. Wendy Fredman, an astrophysicist at the University of Chicago, said the next rungs are added using side readings alone. Then astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Ree and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 km per second per megapark when compared to the Planck measurement. However, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant seeds to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it at 6.5 m wide. Webb's mirror is almost 3 times the size of Hubble's which is just 2.4 m wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths by comparing seeds measured by James Webb in the galaxy NGC 4258 with bright-type IA supernovas. Another standard candle because they all burst at the same absolute luminosity in remote galaxies. Reese and his colleagues arrived at a nearly identical result, 73 km/s per megapark. Other measurements, including one made by Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch red giant stars, and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 kilometers per second per megapark. A separate result using the bending of light also gave a value of 73 kilometers per second per megapark. Cosmologists were left reeling, according to Ronan Kai, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension. The CMB temperature is measured at the level of 1% precision, and the CIA distance ladder measurement is getting close to 1%, so a difference of 7 km/s, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmology into factions, chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavai Institute for Theoretical Physics, KIP in California, only caused more frustration, as the late Vera Rubin, who discovered evidence for dark matter, said, "At the time, nobody wanted to let go of their toy." All of the people involved believed so strongly in their own results and so strongly in the fact that their observations and their measurements were done correctly. It just left people wanting to figure out how do I explain this. In February 2023 with James Webb and another independent Hubble distance ladder result confirming the Hubble tension, cosmologists are left with three possible explanations: measurement errors, new physics, or some combination of the two. Kai explained that most of the data supports new physics. The simplest and most popular hypothesis is that dark energy behaves differently today than it did in the early universe. If dark energy was strong at one time and then faded away, it would make the universe look smaller when we look back in time to the early universe, making the expansion rate appear faster. Today there are other explanations, such as the possibility that there are two kinds of dark energy, or that dark matter interacts with light, but these explanations introduce complexities that cosmologists are wary of. Without further data, dark energy and dark matter aren't the only mysteries James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's revolutionary new imaging technology enabled it to see galaxies form just 300 million years after the Big Bang. However, while peering at the universe's origins, astronomers found that these primordial galaxies are far more massive and evolved than the standard model predicts. Early galaxies should have been full of young hot stars forming at breakneck speed, but James Webb showed many of them were bursting with heavy elements from earlier generations of stars and actively building up bulging cores of supermassive black holes. James Webb's observations have intensified the debate in cosmology by providing precise data that confirms existing discrepancies and reveals unexpected details about early galaxies, resolving the Hubble tension and understanding these early galaxies might require new physics or a significant revision of the standard cosmological model. The pursuit of these answers is one of the most exciting frontiers in modern astrophysics. The James Webb Space Telescope JWST has not only revolutionized our understanding of early galaxies but has also opened new avenues for exploring fundamental questions in cosmology. Its infrared capabilities allow it to peer deeper into the universe than ever before, capturing light from some of the earliest galaxies formed just 300 million years after the Big Bang. These observations have challenged the conventional wisdom about galaxy formation, suggesting that early galaxies were not just simple young structures, but were surprisingly mature, containing heavy elements and harboring massive black holes at their core. This discrepancy between theory and observation raises profound questions about the mechanisms driving galaxy evolution in the early universe. It hints at processes that were perhaps more rapid and efficient than previously thought, leading to the formation of galaxies with unexpectedly complex structures so soon after the Big Bang. Moreover, JWST findings have exacerbated the long-standing puzzle surrounding dark matter and dark energy. These elusive components comprising the majority of the universe's content remain poorly understood. Dark matter, which interacts gravitationally but not electromagnetically, plays a crucial role in shaping the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. Despite extensive efforts, its precise nature and composition remain elusive, prompting ongoing searches through direct and indirect detection methods. On the other hand, dark energy, responsible for the accelerated expansion of the universe, presents an even more enigmatic challenge. The standard cosmological model posits dark energy as a cosmological constant consistent in its properties throughout spacetime. However, discrepancies such as the Hubble tension suggest that dark energy's behavior may not be so uniform. Alternative theories propose dynamic forms of dark energy that evolve over cosmic time, potentially influencing the universe's expansion rate differently at various epochs. Solving these mysteries requires not only advanced observational capabilities, like those of JWST, but also theoretical frameworks that can accommodate new data without abandoning the successes of the current model. Astrophysicists and cosmologists are exploring various hypotheses, from modified gravity theories to exotic particles and interactions beyond the standard model of particle physics. The implications of JWST discoveries extend beyond cosmology into broader astrophysical questions, including the origins of life up supporting planets and the conditions necessary for complex chemistry to arise in the universe. By studying distant galaxies and their environments, astronomers hope to glean insights into the conditions under which Earth-like planets may form and evolve around other stars, offering clues to the prevalence and diversity of life in the cosmos. Looking ahead, JWST promises to continue pushing the boundaries of our cosmic knowledge. Its unprecedented sensitivity and resolution will enable astronomers to study the atmospheres of exoplanets, characterize the properties of distant galaxies in exquisite detail, and probe the earliest epochs of cosmic history with unparalleled precision. These endeavors not only deepen our understanding of the universe's past but also pave the way for transformative discoveries that could reshape our understanding of physics, astronomy, and our place in the cosmos. As JWST begins its operational phase, astronomers eagerly await new insights into the universe's most profound mysteries. Whether it's unraveling the nature of dark matter and dark energy, understanding the formation and evolution of galaxies, or exploring the potential for life beyond Earth, JWST stands poised to revolutionize our understanding of the cosmos in ways that were once unimaginable. In conclusion, the convergence of advanced technology, theoretical innovation, and rigorous observation promises an exciting era in cosmology and astrophysics. JWST's contributions are set to be pivotal, offering a clearer glimpse into the universe's earliest moments while challenging and refining our fundamental theories of its structure and evolution. As we embark on this journey of discovery, the mysteries of the universe await exploration, and JWST stands at the forefront, ready to unveil the secrets of our cosmic origins and destiny.